Hello everyone, I'm Jwbe. I'm a master's degree student at Federal University of ABC. The title of my presentation is a proposal for 3D electron-anatomical mapping software based on benchmark from current clinical systems. What is 3D electron-anatomical mapping and why does it matter for electrophysiological studies? By these kind of systems, we are able to create the anatomy of the chamber of interest and we are able to identify atrial and ventricular arrhythmias, particularly complex arrhythmias such as atrial fibrillation and ventricular tachycardia, and it provides us precise localization of abnormal electrical activity. And the system is able to have the integration of heart geometry and electrophysiology for real-time guidance. Mainly, there are four kind of electron-anatomical mapping systems from different brands that are being commercially used at hospitals and clinics nowadays. In this figure, I'm showing different types of diagnostic catheters. There are different sizes, different number of electrodes, and different characteristics. In this slide, I'm talking about radio frequency cardiac ablation. So at hospital and clinics, they use RF generator and they use RF ablation catheter type, which usually has 4-pole catheters, and the catheter by physicians enters to the femoral vein of the patient and it reaches to the heart and chamber of interest, as we can see in this figure. So this is one specific type of diagnostic catheter, which is called circular catheter, and this is RF ablation catheter, which is located in the left atrium. Now I'm going to talk about catheter localization technologies. So the first one, which is magnetic base. So how does this technology work? We should use a magnetic field frame under the table of the patient, and it produces 3 ultra-low magnetic fields between this value, which is detected by sensor in the tip of the catheter. Now I'm talking about impedance-based technology. So this technology uses low-amplitude AC current between surface patches and catheter electrodes and measure voltage differences to calculate impedance along 3 different axes. Nowadays, most of the systems use a combination of these 2 technologies for catheter localization, which is called hybrid. It is a mixture of magnetic and impedance field. Now I'm talking about my objective. My main objective is benchmark analysis, which is conducting a comparative review of commercial 3D electron-anatomical mapping systems to identify their key biomedical, computational, and clinical features with current electrophysiological practices. And specific objectives consist of catheter localization and tracking, signal preprocessing, mapping methodologies, and 3D anatomical modeling. So about methodology, I divided in 3 different sections. About preprocessing, which is the same for all of the 3D electron-anatomical mapping systems. They use the same procedure, but only the location of the patches might be different for each system, but generally they use the same procedure. Here, as you can see, all of the electrodes for ECG, we can see the patches which are located on the body surface of the patient. If the system has magnetic field technology, magnetic-based technology actually, we should also put the magnetic field frame under the table of the patient, which should be in the correct position as well. Here, I'm talking about inside a system and different types of catheter that this system has. So there are 2 types of catheters here, HD-grid and HD-grid X, which they follow the contact mapping technique. Here I'm talking about Carto system, so it has this kind of catheters, octa-array, this type of catheter with different number of electrodes, and pent-array as well, but all of them work with contact mapping. Arrhythmia, this system has this specific type of the catheter, which is called Orion. It has 64 electrodes. It also uses contact mapping technique, and it works with magnetic and impedance, which is called hybrid technology. In this slide, I'm talking about ACQ map, which has a specific catheter, because this system, the primary method which uses is non-contact ultrasound mapping, because the catheter from this system has 48 ultrasound transducers, and it is able to create the anatomy without contacting the tissue. So there are 3 types of filtering for ECG signals, unipolar and bipolar electrograms for all of the systems. Now during the process, so the first step that the physicians start to do during the process is using 10-pole or 20-pole catheter, putting in coronary sinus. As I'm showing you here, this is part of the coronary sinus in the heart. Here I'm showing you a video from inside during the process of creating the anatomy using HD-grid catheter from inside, and we can see that the catheter is creating the anatomy of left atrium in this case. Here we can see that the left atrium anatomy was completed, so it's ready to analyze, and at the same time we can see the electrical signals of the heart as well. And here in this video I'm showing you when the physicians start to do the ablation. Here about Carto system, as I told you before, this system is able to integrate imaging modalities such as echocardiography that we are seeing here to create more precise and more accurate anatomy with giving more information to physicians to be able to have the best decision for the patient. Here I'm showing you from arrhythmia, so I'm showing you from the first step to the last step that this system uses to create anatomy, and here it's the general window from the system, so we are able to look at the signals, look at the map, different types of mapping to be able to analyze. And here I'm showing you from ACQ map about post-processing, which consists of 3D anatomical reconstruction, map rendering and color coding, interface tools, and editing. For inside, so when we complete the procedure of creating the anatomy using the catheter, after that we are able to edit the anatomy and separate each part, each region of the heart, and put a label for them to make them easier to compare and analyze the data for the physicians. Here we can see different types of is the same. We are able to edit the anatomy, make them smoother, and also we are able to create different types of mapping as well. Arrhythmia as well. So we can see the different types of mapping is in this system. And here this figure from ACQ map that it shows us the rotational activation, focal re-entries. So the part of my result, I can show you here from inside. So about the signals, it is able to show 12 lead ECG, 10 bipolar coronary sinus catheter, 24 bipolar HD grid catheter signals, and 2 bipolar radio frequency catheter as well. So at the same time, you are able to see all of these channels. Another figure that I'm showing you to have a general overview about the software of the system. Here is one example that is part of my result. So I'm showing you one voltage mapping from atrial fibrillation case, and also this patient had atrial flutter as well. But you can see the color coding. The purple region shows the healthy tissue, and the colorful region shows transitional tissue, and the gray region shows scar tissue. Now I'm talking about arrhythmia. So we are able to see the signals from ECG, 10 bipolar coronary sinus catheter, 32 bipolar Orion catheter, which is one of the diagnostic catheter, and 2 bipolar ablation catheter. Here, this just an example to have some overview about the software of the system, and it is one example of atrial flutter case, which is part of the right atrium. In this video, you are seeing the voltage map from arrhythmia system, and here you can see the post-ablation of atrial fibrillation, which the physicians isolated all of the pulmonary veins to eliminate atrial fibrillation. And now I'm talking about ACQ map system. Again, we can see 12 ECG signals, 10 bipolar coronary sinus catheter, 24 bipolar the specific catheter from this system, and 2 bipolar ablation catheter. And in this video, we are seeing the propagation mapping that this system has, and it shows us the electrical propagation inside of the left atrium in this case. And if I want to show you generally how number of bipolar channels do we need, I can say that we need 12 ECG channels, 10 bipolar coronary sinus catheter. If you want to use circular, or which is called lasso catheter, we need 10 bipolar channel for that, and 2 bipolar ablation catheter. So in total, we need to have at least 34 bipolar channels. So my project is still in progress, but I'm going to define the criteria for the core subsystem, aiming to ensure reproducibility in software implementation and to foster interdisciplinary collaboration among biomedical engineers, computer scientists, and electrophysiologists. So in the future, I'm going to conduct more comparative analysis between the existing commercial systems. I will finalize and validate subsystems and specifications. I will optimize software algorithms to enhance efficiency and stability, and I will integrate additional data sources to improve spatial temporal resolution. This is my references, and thank you for your attention.